Welcome back, everybody. Hopefully you got a chance to watch the lightning talk that we played during the break. We'll be showing these in between sessions, and each of the videos showcases an innovative piece of Turing Institute research in action. If you want to watch these videos in one go or any session again, you can go to the on-demand section in Hopin. Now for our next session. We're talking about AI and energy, from the development of batteries to manufacturing. I'm delighted to introduce your host for today, Dr. Chris Dent. Chris is an associate professor in industrial mathematics in the School of Mathematics at the University of Edinburgh. Since 2007, he's worked full-time in energy systems analysis and currently concentrates on security of supply risk analysis and the use of large-scale computer models in decision-making. He's a senior member of the Institute of Electrical and Electronic Engineering, a fellow of the Operational Research Society, and a chartered engineer. It's over to you, Chris.
Thank you very much, and welcome to this session, everyone. I should just update the intro slightly. So I'm actually now full professor of industrial mathematics at the University of Edinburgh, and also I remain a Turing Fellow at the Alan Turing Institute. So I'm very pleased to introduce this session on AI and energy, where we'll explore a wide range of applications of AI associated with future energy supply. And this will range from matters of how we control the whole energy system in the more complex and uncertain environment that we're heading towards, with very large capacities of renewable generation and other emerging technologies. And also we'll look at some of the applications of AI in design and development of technology and materials. I'm sorry I can't be here in person. I was actually last week in the United States talking with people about AI and energy systems, and only got back to Britain on Monday evening, so I couldn't travel down to London to be at the event in person, unfortunately. Anyway, I think everyone is here to listen to the speakers and not to me, so I'm very pleased to hand over to the first speaker, Gareth Conduit, who is Chief Technology Officer of Intelligence and a Royal Society Research Fellow at the University of Cambridge. And he will talk about towards net zero with machine learning, battery and materials development. So over to Gareth.
The work that we have been doing on developing and applying novel machine learning methods to design both new cells for batteries, but also battery packs, battery management software. So at Intelligence, we've had a real focus on developing machine learning software for the real life use cases of developing new materials, new pharmaceuticals, and new industrial chemicals. This means that we've had to have a real focus on some practical realities. The problem that the data sets that we are handling are almost always sparse. And this is because it's experimental data and not everything has been measured. Also, the data sets are typically very noisy. There's a lot of uncertainty in them due to that experimental uncertainty. We also have to remember that the data sets we're dealing with are very high dimensional. There's always lots of properties of the battery that we need to be able to predict. So therefore, we've had to develop a very generic algorithm that can handle all of these sort of different properties of the battery that we need to handle, but that therefore means it can also be able to cope with lots of other problems in spanning materials, industrial chemicals, and pharmaceuticals. However, it is not all about the clever algorithm. What is also important is that it is really easy to use to empower the actual engineers who will be getting their hands dirty making these batteries. So there's been a lot of focus on getting it to be very easy to use to give an immediate return on investment. Now, the basic setup of our machine learning is going to take in as inputs on the left everything that we would need to know about the battery, everything we can change. So here we show the formulation of the battery, but also there's going to be the processing parameters, the geometry of the battery, and so on. That is passed into the machine learning tool, and out on the right it will predict everything we need to know about the battery, spanning right at the top of the list to the very almost atomic length scales, properties of the materials and the cells, down to the bottom about the when we actually put those cells together in a battery, in a pack, in an electric vehicle, to tell us, for example, the range of the electric car. Now, this means that we are able to address a full gamut of issues to do with batteries, starting out on the left from the materials formulation, designing those cells, through to how to geometrically put those together into battery packs, and over on the right to be able to handle and develop battery management software to get the maximum performance out of your electric car. Now, that all sounds great, but unfortunately life isn't quite so easy in research and development. And just to highlight some of the problems we face, we have here a typical data set, almost a spreadsheet that we would have to handle. In this spreadsheet, imagine each row is a different material, a different battery, and the different columns could be the composition of the battery and also cover its properties. Now, we can first see that there's various white cells in this spreadsheet, and they represent sort of blank data, things that are just not known. This almost always arises in experiments, and it could be because we're using historical data when the experimentalists were interested in measuring some properties of a battery, but not all of the ones that we are now interested in, and so they are missing. It could be because the tests on the battery are destructive, and once you measured one thing, you've destroyed the battery, so cannot measure the other. Or it could be because we've got some in real life data that's been taken at various frequencies, for example, the temperature of the battery, the voltage and the current, and when taken at different frequencies, necessarily some things in there and some are not. Now, another big problem that we face is that the data is very noisy, which we've highlighted here in red. The data is going to be noisy because it's got some experimental uncertainty on it, and sometimes we know what that uncertainty is, and sometimes, even worse, you don't even know what that uncertainty is, and you can have some outliers in the data, as shown by the deep red. Now, a priori, we don't know what the outliers are, we don't know what the uncertainties are going to be, we don't know what the noise is, and so we need a machine learning method that's going to be robust and be able to take in all this data and be able to skip around things that it thinks could well be outliers. Now, another issue that we're going to face is that not all the data are numbers. For example, some of the data could be categoricals, or as we show in the bottom right of the slide, we can even have graphs, which could be, for example, a property of the battery versus time or the number of cycles. Now, we could encode that as many different rows in the data in the spreadsheet, but that is both a very inefficient encoding and also can place undue weight on data, so if you happen to have more points in a particular graph. So therefore, we really need a seamless way to be able to handle this graphical vector data. And all this means that we're going to have a large number of columns in our spreadsheet, so we're going to need a machine learning method that's generic. It can handle all of these different kinds of data simultaneously and be able to work very quickly over them. But that's just one of the problems. That's the technical problem, but there's also going to be some real-life problems that even if we can solve those and get a really good algorithm, then that still may not be enough for those end users. We classify users in two types. Over on the left-hand side of the slide, we have data scientists. So these are people that are probably familiar with various methods of machine learning, perhaps not one that can handle the sparse data, but they need to, once they've trained up the model, they need to then be able to promulgate it to all of the engineers in the company. If there are 1,000 engineers in the company, then it's going to be non-trivial in order to give them access to the correct models. And so you really need a robust enterprise software solution. And over on the right, we've got our other kind of user who are the real-life engineers. They're not really that interested in machine learning. They don't want to be doing any coding in Python. They just want to have access to a machine learning model that's really easy to use and will tell them the information they need, i.e. how to make new materials and give them scientific insights into the data that they have. So to solve these problems, we have developed the Alkamites Method. It came out of my research group at the University of Cambridge and was developed in league with several industrial collaborators. So it's really set up to be able to handle this sparse and very difficult data. And to give you a hint about how it does that, we've got this flow chart on the right that has been taken from one of our peer-reviewed papers, where at the bottom you can see a little cycle. And this is one in which it's actually imputing, it's filling in the gaps. It takes the initial sparse data, it makes some guesses for the missing values, so it can then use those numbers as inputs for machine learning, makes better predictions for the missing values, and then cycles around recursively until it converges onto what it thinks is the best prediction. Now, once we got this set up, we're not only going to make good predictions, but also we can understand the uncertainty in our predictions, uncertainty that could arise because of that underlying noise in the training data, or it could arise because we're extrapolating a long way. But with the uncertainty predictions, we can understand where our model is reliable and robust, and so give the very best advice to those end users. Now, of course, it's not just all about the algorithm. What is also important is that the interface forwards is going to be easy to use. So I've got here a few screenshots of how this can be set up, and we can see that we can give access to the research scientists, to the engineers, to not only good quality predictions, but also to the scientific insights, to an interface for them to design new materials and identify outliers in their data set, and so on. So with all that set up, we're now ready to look at a couple of case studies, and I've got two here where we've been working with battery companies. And the first is on the very almost atomic scale about developing new materials, in this case an electrode for a battery. This project was done sponsored by the Faraday Institution and was also done alongside academic collaborators at the University of Birmingham and also with a company called ANSYS. So in this project, we were challenged to try to design a new graphite electrode that would have better D30 capacity and at the same time a high active mass. Now we can see those properties plotted in that graph on the left, where in black we've got all of the currently existing experimental data that we could train off, and a kind of red trend line through those. So that was the training data that we had. We could then train up a machine learning model, ask it to design this battery or electrode that would give us high capacity. And what we predicted is that blue triangle on the right-hand side with, you can see, the uncertainty in our prediction. We can also see our collaborators at the University of Birmingham kindly went off and made this material, tested it, and there we can see the result of their measurement by the orange triangle, where we can see it's within our uncertainty, and it's a significant improvement on other existing materials. And so if you want to read more about that, there's a reference to a paper down at the bottom of the slide. And for our second case study, I've gone right to the other end of the length scale, and this is a project that we did alongside Nanyang Technical University and A-Star over in Singapore, where we're exploring how machine learning can be used for within often electric vehicles to actually do battery management software, to tell us, for example, what's the remaining range of my electric vehicle, which cells within my overall battery pack in the vehicle are showing more wear, and so perhaps I could temporarily turn them off and place more emphasis, load on more healthy cells, so that we can get the overall maximum life out of our battery pack. How long until the next service for the electric vehicle? So we wrote this wonderful Nature Machine Intelligence paper about that, and I'd really invite you to have a look, but it shows really how powerful machine learning can be over other software solutions. Now, as I said, our methodology is completely generic. It's really a methodology for handling sparse data. And so there's a wide range of other companies that we have been able to work with. I'll just show a few of them here. There's a lot of companies that work with in designing new alloys and processes for additive manufacturing. And then down in the bottom middle, we've also done an awful lot of work with pharmaceutical companies in designing new drugs. And actually, you can see there the chemical structure of one of the drugs that we designed and then went on to be synthesized and its activity verified. And so we're really excited about the methodology and really driving forward in the future to almost revolutionize materials to have a real uptick in the usage of machine learning. So with that, I'd like to summarize. I hope I've shown you today how we have been developing our Alkamite machine learning methodology with a real focus on real-life materials data, handling sparse data, handling uncertainties, and high-dimensional data. Then I've shown how we've been able to already apply that in the battery domain towards that goal of net zero, of both designing new materials for individual cells, right up to developing battery management software for use in, for example, electric vehicles. With that, I'd like to thank you all again for coming along, and I hope there's a couple of minutes for questions. So thank you.
Right, thank you very much for the presentation, and I'd like to remind everyone in the audience that you can ask questions through Slido. So unfortunately, I don't actually have any questions in Slido yet, but I do have one myself. So you referred to users of the AI tools not necessarily being expert AI people themselves, and this question of how AI and data science methods are used in practice in organizations when not everyone lives and breathes AI and data science methodology like you or I might do. I'd be grateful for any further reflections that you have on how the skills fit together, how the communication within the company is done, how this how the use of AI tools fits within the organization in this context that maybe other organizations, other people might find some useful learnings from your experience.
Thank you very much, Chris, for the question. I think this is absolutely key in order to make machine learning a really practical reality. In fact, there's two things to sort of reminisce on here. One way that several of the companies we work with function is that they would have one or two sort of data science, machine learning champions, and they would be the ones that would sort of own the database, manage the database within the company. They would sort of permit data to sort of enter it. They've got a budget to try to sort of get data out of dusty filing cabinets and encode it all, and they would be the ones that would train up the machine learning tools and then, or machine learning models, and carefully test them. And then there's a second type of user that they could deploy the models to give them access to the model to make predictions based on it, but not to train the models up themselves. And of course, when they are licensing these machine learning tools, it's often the case that the training part of it is more expensive and difficult to do, and more computationally expensive than it is for the users of the models. And so that way works well with their sort of business plans. And I think the second part of the answer is of how do we make the machine learning really appealing to those end users, those scientists. And I think that is by really trying to speak their own language, that the scientists are well used to plotting graphs of sort of y against x, of property versus some of the inputs. So can we also deliver those plots to them? They are used to, for material selection, seeing Ashby plots. So can we also plot an equivalent and display that to them? They're used to, when analysing the sensitivity of models, to sort of understand the local gradients in which directions the model's steeping. So can we supply those to them as well? And by speaking the same language as the tools they're already using, perhaps of plotting little graphs in spreadsheets, then we can also get a real uptick in adoption.
Great, thanks very much. And I've got a few questions now. I'll take the first two together. We've got about 2 minutes remaining in questions, but I'll take the first two together because they're closely related, and then see how we're doing for time. So first two were, what sort of algorithms do you use for optimizing battery usage in BMS software, and the second was how was the Alkamite methodology validated in the real world?
So for optimizing this at the battery management software, so we were testing it on our machine learning methodology, but there's several streams of data that we're going to be taking in. We've both got access both to the experimental data, though that is, of course, is very expensive to obtain and is quite sparse. And then we also have access to various sort of analytical models that sort of already exist for the performance of batteries that expensive, so maybe very microscopic chemical models, finite element models, and also some more sort of rule of thumb. And we can also get results for those and make a very dense data set out of them. And then by the way that our machine learning at least works, we can then hop in between them, that we can go from the inputs to these analytical type predictions, though we could do so quicker than an analytical prediction, but we've got loads of those results, train a very detailed model, and then in a second step do the correction factor on top of the analytical models to get to that final experimental quantity. That hopefully the correction is relatively simple to do, so you don't need as much data to characterize it. So that's just a sort of, in essence, about at least our viewpoint on how to handle sparse data. Now, in terms of how do we know whether our models are working well, well, the first thing that we'd always do is you do the very standard machine learning approach of cross-validation, which in brief is you've got a big data set provided, and that you would hide some of it in top secret, train the machine learning tool on the rest of it, and then make predictions of that blind validation set, and then compare how well you can predict those numbers. So that would, sort of in effect, it's almost like doing a new experiment on those numbers to see how well you perform. But then I think the real validation is in the materials that we've actually designed for our customers. So I showed just a couple of the projects we've done on today that sort of went on to independent validation. But then there are loads of others that if you can look at our website, you'll see that we started out doing a lot of work with Rolls-Royce, designing various alloys for them. Then we've got all the drug design work and much others. So I think it's that actual work for customers that they've allowed us to write up as academic papers where they did the independent validation that provides the real proof that machine learning does work.
Great, thank you very much. And that was perfectly timed to finish the last sentence on 19 minutes, which is where it was scheduled to hand over to the next speaker. So juggling multiple windows that I'm using to manage this session. The next speaker, I'm very pleased to introduce Andrea Karlova, who's a research student at UCL and a machine learning scientist at April 19 Discovery, who's going to speak on machine learning in perovskite discovery. So very pleased to hand over to Andrea.
Hi. Okay, so when I think about the March 2022, I think it's been a true parade of the black swan events, right? We have been seeing murdering of the innocent civilians by kind of powerhouse which economy is based mainly on the old-fashioned fossil fuels. On 1st March came the report out of ICBP, which reported about the irreversible changes caused by the climate change. And you know, all these things are actually caused by the way how we are harvesting the energy. And the fossil fuels are the main contributors to the climate change. Well, you know, we can do better than that. So the goal isn't to scare you at the beginning of the talk, but the goal is to really show you what is our potential. And think about the sun, right? So the sun provides us with the unlimited source of the energy. There is about 10,000 times more energy available than what is our demand, our consumption. More precisely, the sun produces in 1 hour 174,000 terawatts of the energy, which is roughly a yearly consumption of the entire planet. And I think that we have been doing quite a great job when it comes to the harvesting this energy. But obviously, the solar energy is being the harvesting is covering, say, less than 1% of the overall energy harvesting. So there are great limitations and the great potential. This is a chart from the National Renewable Energy Laboratory from Colorado. And these guys have been tracking the development for a very long time. So I think the first solar, you see that the energy, the technology on its own is pretty old. It's from late 70s. And it's been like really in the last decade when we see the massive spike and the development. The development is not only in the efficiency when it comes to the classical silicon-based solar cells, but mainly we see that there has been emergence of the completely new materials. And I think that I would like to point you to the orange line in the chart, especially the one with the circles with yellow centers, and over there that's the perovskite materials, which I'm going to be talking about mainly in this talk. And you see that there is quite steep spike. One of the main contributors actually to this is a UK-based company. We also see that in the violet. There is the way how you can increase the efficiency is really by having a multi-junction solar cells. Okay, so there is still 90% of the solar cells of the material used as silicon based. So when it comes to the silicon, it's it's been well explored, it's been heavily funded, it has its quite big downside, and the downside is that it is not very. It has a big carbon footprint in a way, because you need to mine the material, you need to transport the material, and the manufacturing of the wafers is around 1400 Celsius. So it requests a quite non-trivial amount of the energy. On the other hand, when you think about the revolution which is coming in the solars, and pretty much with the materials like perovskites, which are, say, for example, also pioneered by the Oxford photovoltaics, you need roughly around 35 kilograms of the perovskite material to produce the same amount of the energy as 7 tons of the silicon. So think about the carbon footprint when it's scaled. But it's not only advantage of that. Okay, nice. Let's look into the crystals and their properties, right? So as I said, the silicon is well explored, whereas the perovskites, it's really emerging materials which still needs loads of research, but has a large potential. When you look at the crystal of the silicon, it's pretty much just one type of atom which is there available. Whereas perovskites is technically anything which has the crystal structure which you see on the slide. And I think the main thing about here is that the silicon is quite bulky. The manufacturing is quite costly. The band gap which you have with the silicon is, say, 1.12 electrovolts, and that's roughly it. So if you want to, for single p-n junction, you will have the 33% of the power conversion efficiency. Now, this is true for all solar cells when it comes to single p-n junction. But the real thing is about, or the way how you are improving the efficiency, is that you are layering different different materials with so you are layering different junctions where you can tune the band gaps. Now this is exactly what you can do easily with the perovskites, because so first of all the manufacturing comes at the temperatures which are less than 100 Celsius. So I mean, pretty much think about the cup of tea, right? The materials are extremely lightweight, and so you can produce them in a very thin films. And when you're thinking about the manufacturing, you can pretty much just print screen them, or you can you can just like paint them on the plastic, and that gives you enormous amount of potential for use it in the product. But as I was speaking about the tunability, about the increasing the efficiency of the solar panel, it's really the tunability of the band gap, which the perovskites allows you to achieve. So again, if you would be layering infinite amount of the PN junctions, you will end up with the theoretical limit around 86.8%. So it's hard to achieve that when you would be layering infinite amount of them of the layers, but at the same time, you know, it's very hard to achieve this with the silicon, right? Because think about the bulk. At the same time, with the perovskites, you can easily layer different layers of thin layers of the material with a different band gap. And so even just combining the silicon with the thin coat layer of the perovskites gives around extra 10% of the power conversion efficiency. So speaking about the band gap, which is like really crucial for not only for the photovoltaics, but mainly also for the machine learning solution which we are looking into. So when you think about the two electron, when you think about the two atoms, when they are in their single states, or when they are in the separate states, the electrons would be in a discrete energy levels. And then once they start to bond, I mean, they're either the orbitals starts to sort of deform, and they start to overlap, or depending on the spin orbital, they might also they might be in the anti-bonding positions. Now, how does this work in the material? Because in the material you have a large amount, you have millions of the atoms, and they are organized in the crystal in say lattice-like structures, right? So in that case, these atomic orbitals starts to overlap, and they are forming sort of nearly continuum layers of which form the different bands. So rather than having a single energy states, you are having these bands of the energy states. And now you have the valence band, where are the electrons in their sort of a normal state. And then you have the conduction band, which is the unoccupied, the lowest unoccupied energy state, where the electrons would move once they get some amount of the energy. And if you have, say, metals, in the classical metals, these two bands are overlapping, so there is like a very good conductivity. If you have the insulators, this band gap is really large. But what really is important for us is when you have the band gaps of the sufficiently small size. So just to quickly explain how exactly why we need the band gap and how we can tailor the efficiency of the solar cells. So as you have the photon coming into the material, it gets anything which is less than the band gap value is pretty much just passes through, so it's not being used. Anything which is exactly at the band gap value is being used, and it's being converted into the you can convert it into the electricity already. Anything which is above the, any sort of spectrum of the energy which is above the band gap value is actually being sort of wasted because it's being converted into the heat. And that's majority of the energy which comes from the sun and the solar panels is being converted into the heat. So really by tuning and engineering and finding the materials which has these different band gaps, as you see, you can target the larger spectrum of the solar beam of the energy which comes, and that's why you can harvest sort of more energy in a better way. Okay, so what are the perovskites exactly? So we have the crystal, and usually the B side of the crystal and the C side of the crystal, these are sort of, we work with the metal halide perovskites, so we would be having the halogen group for the C side and the combination of the elements from the halogen group, and then on the B side usually you would have something like germanium, tin, or lead. But where's the interesting game changer? It actually comes with the A side, because in the A side you have a large amount of potential. So the one which is mainly explored is metal ammonium or formamidium, but you can pretty much put there any organic cell. So we just to quickly sort of motivate a first sketch proof of idea, which we were doing the virtual screening, motivated by the drug discovery, which we published at ICML climate change workshop last year. So over here, the task is like we have some molecule. We somehow need to we look for some kind of molecular representation which we can pass to our machine learning model, and on which the machine learning model can learn. Now, funny enough, if you just take a simple Morgan fingerprints and you would compress them, you can create a chemically semantic latent space. And this is actually quite helpful because when you think about the large space of the potential molecules from which you can choose, that really it's good to just have a sort of focused regions. So how big this space can be? It can be roughly 10 power 60. Now, this is sort of our sort of more final design of the system, and you pretty much start by selecting molecules from the organic molecules from the large database, and you somehow would like to pre-process them. So the way the thing is where the machine learning can play a big role is either in organizing the latent or the space of the molecules itself. So you can really better select the molecules, because even if you would be looking at some, you have say 1 billion molecules in the database, and if you would like to organize them according to their chemical properties, that is computationally too costly. So really, just some kind of quick solution is helpful. But the molecules in the database are often represented as small strings, which gives you nice mapping into the two-dimensional graphs. But that's not really what you need for your ab initio computations, where you really want to computationally assess compute the band gap. So you need to have some kind of 3D conformer. You'd like to compute the 3D coordinates, and the more precisely you do it, the more you can speed up your computation. So this is one of the regions where the actual AI helps you quite a lot. So for us, what is the most important? If we sort of pick up some kind of a large set of the promising candidates, then you need to assess their formability and their thermal stability. And so for that, there is you can train the machine learning model, And in our case, I have been looking into using the graph neural networks. So we have when you think about a crystal, you can represent it as a graph, and you have the atomic features, you have the bond features, and then you have the overall crystal features. But at the same time, I have been also using the information coming from the cheap DFT computation. So I have the electrostatic potential and extract the surface features from the electrostatic potential, and then pass it through a couple of attention layers, and like a sort of smartly designed, and that gives us reasonably precise estimates of the band gap, and having that. Then we need to pass it again to the DFT computation and verify with a more expensive and more precise exchange correlation functional. What is the true or closer to reality value before you can actually offer it to people in the lab. Okay, so when you think about the future, I mean. You can use the solar materials for pretty much all sorts of solutions. So the slides which I'm showing are already existing solutions. But basically, if you would put these thin films or some kind of solutions on, say, every building, on every warehouse south-facing in UK, it would cover the overall energy efficiency. So. I think there is an exciting future coming. I think that's all. Sorry, I forgot about my collaborators, which is very embarrassing. I would like to mention that this is actually a collaboration with the University of Surrey, and it's been really exciting to actually work with these guys because they are more technically focused, and it's been great pleasure. That was my last slide.
In the interest of time, we're going to need to move on, straight on to the next speaker, who is Sam Young, practice manager for data science and artificial intelligence at the Energy Systems Catapult. And he's going to speak about artificial intelligence in the energy system. So over to you, Sam.
AI is sticking
Right, I think we might have a little technical issue here. So just to confirm, I'm very pleased to hand over to Sam Young as the next speaker, and hopefully the ownership of the presentation will switch over to him.
AI is sticking to its comfort zone. It's avoiding doing the hard bits of energy. Imagine AI doing its sales pitch to the energy sector. Hi, I'm AI. How can I help? I can do image processing. You don't have any images, do you? Oh, you don't have large tabular data sets I could look for correlations in, do you? Would you like me to build you a chatbot? I can do chatbots. What's that? Predict the future. I'll get back to you on that. You see, what we see in the energy sector is a lot of applications of AI to problems that AI is good at in other sectors, without necessarily addressing some of the core challenges in the energy sector. And many of those core challenges involve time series, because ultimately the energy sector is all about making sure we have the energy we need on a second-by-second basis. But the problem for AI is that one of the fundamental assumptions of most machine learning algorithms is violated with time series. Most machine learning algorithms fundamentally assume that observations are independent, that the order that you process the data in doesn't matter. And yet with time series analysis, that is obviously not true. If I said to you, how much energy are you using now? And how much energy do you think you'll be using in 1 minute's time? Those two are going to be pretty strongly correlated. In fact, the whole point of time series is that there's lots of information in the time element of the data. And so I want to introduce you to some of my good friends, time series problems in the energy sector that are fun to hang out with. But before I do, imagine what happens when you meet someone for the first time. What do you do? Now, like it or not, research shows that you judge them based on appearance. And the same is true of data. We judge it based on its appearance. We visualize it. Now, with time series data, it probably looks something like this. A great big spiky chart with ups and downs. How exciting. And you can see some patterns, but can you really understand them? And if you're fortunate, you get some kind of decomposition like this, where you've got some trend and some seasonality and some noise. But it's hard to really understand the seasonality in detail. And in fact, that's one of the real challenges of time series analysis, seasonality. Intuitively, you know that the time of day and time of year will make a big difference to energy usage. But actually quantifying that isn't easy. In particular, daily variations are hard to visualize sometimes. So one of the things I came up with in the course of my work is this, a clock plot. You can see the energy usage plotted on a 24-hour clock face, and you can segment that by different things. For example, you can see how it varies over the day across different seasons, like is shown here. And it's a really good way to visualize within day patterns. And it works best if you have a lot of variation within the day, so you don't just get circles, and allows you to compare lots of different things. Your eyes spot differences in the shapes, like we can see with 16 homes here. If you want to give it a try, the ClockPlots Python package is available for you to install and use. But the point that I really wanted to make is that good visualizations can unlock understanding. So if you know of good visualizations of time series data, I'm always keen to see them, share them with me. So that's what happens when you meet a new person. Now let me actually introduce you. The first time series friend I want you to meet is demand. Electricity demand and its identical twin, or almost identical twin, supply. The whole purpose of our electricity network is to ensure that wherever there's demand, it's equally matched by supply. Whenever you flick a switch, the electricity flows to you. Okay, so you look at that curve and go, forecasting demand and supply. How hard can it be? Surely AI can manage that. Well, hold on. It's a bit more complicated than that. You see, we don't just care about the national level, a single time series, but what we actually care about is balancing supply and demand across the whole country. To a hospital, to a school, to your home, everywhere needs to be balanced. And so maybe a way to think about it is as a hierarchy. You have your whole country, then your different regions, and then different parts of the net, all the way down to individual buildings. And maybe if we just forecast the individual buildings well, then add it all up, it'll work. The bad news is that forecasting time series at the bottom and adding them up doesn't work very well. The errors at the higher levels quickly become quite large. The good news, though, is that there's been some promising work here with AI. The M5 forecasting competition a couple of years ago looked at hierarchical demand in a shopping context. How many of each product would be sold in a particular store or area? And for the first time, machine learning performed 20% better than statistical approaches. I'm currently working on applying that to energy time series. I'm running a challenge with Western power distribution on how to forecast and particularly fill in missing gaps in a hierarchy of energy time series. If you want to get involved, the competition is open now and the link is on the slide. But I'm going to let you in on a secret. Energy is more fun than shopping. And by more fun, I obviously mean more difficult. In what way? Well, there are several. Let me give you a few. The first, and maybe some of you here are mathematicians, you'll enjoy this. You see, you're used to 1 + 1 being 2. One car plus one car makes 2 cars. Stick them on a transporter, send them around the country, and you've still got 2 cars. Unfortunately, electricity doesn't quite work like that. In fact, what we find is that 1 + 1 is somewhere between 2.16 and 2.2. Why? Because as we transmit electricity over the wires, some of it is lost to heat. And therefore you have to put in more than you get out at the end. And that means that with hierarchical time series, it just doesn't add up, and you'd never expect it to. And those losses vary based on things that themselves vary with time. Air temperature, wind speed, how much electricity you're moving, how far you're moving it. And so you can see it becomes a bit more complex. Sorry, I mean a bit more fun. So maybe you're thinking, okay, but we can still kind of map out a graph of the network and we can apply some weights to the edges to allow us to have losses. And maybe you come up with in your mind kind of something like this. You probably don't come up with something that complex, but this is the actual UK electricity transmission network. And you can see it's quite complicated and it's got lots of closed loops in it, which makes the maths much harder. But worse than that, the problem is you don't have a nice static hierarchy. What you actually have is this. Bits of the network switch in and out constantly. People add new things like an electric vehicle. And so you don't actually have a nice static graph that you can run your analysis on. You have dynamic graphs changing all the time. Okay, so it's a bit more complicated. You've got lots of time series. They don't all add up, but you kind of want them to. And now how they're connected together changes over time. But of course, we're not finished there. You see, we also need to overlay it on the country because location matters. Hang on, Sam. Why does location matter? Well, because of weather. You see, wind and solar generation don't just depend on weather, they depend on local weather. You can't just take the average wind speed for the country. You need to know which hill the turbines are on and how windy it is now. And that really is a pain. And in case you think we're finally at the maximum complexity we're going to have to cover, let me disillusion you once more. We need to balance not just the electrical power flowing through the system, but the voltage and frequency of the system as well, so that our appliances can cope with it. And so what we have is an incredibly complex interconnected system that's changing over time, is dependent on weather. We need to forecast lots of different points, and we need to manage not just one metric, but lots. That's the challenge. Why bother solving it? Well, there are many reasons, but I'll focus on just one. The electricity system operator on our behalf has to ensure that the system is always balanced. And in order to do that, they need to make sure that they buy enough electricity and that it comes onto the system at the right time in the right places. And if they know how much they're going to need in the next second, the next minute, the next hour, then they can buy just enough and no more. But the greater the uncertainty around the forecast, the more they have to pay to cover that uncertainty. And that costs us. In the last few years, renewable generation has begun to play a bigger role in our system, and the costs of balancing the network have risen sharply. Generation being dependent on weather just makes supply much less predictable. In fact, it may surprise you to know that we're sometimes paying wind farms to not generate electricity because we have too much. And that points to the final layer of complexity I wanted to mention. In the past, we've altered supply to meet demand because demand varied and supply was quite constant. But in the future, it may be cheaper for us to alter demand to meet supply. And in fact, there's a nascent market in demand side response where people are paid to alter their demand. And that presents its own challenge. If you're paying people to alter their demand, how do you work out what their demand would have been before you paid them. So how has AI been used in all of this? Well, it won't surprise you to know that we don't have an all singing, all dancing AI optimizing the whole system for us, but we've been attacking it from a number of different angles. A great example is Open Climate Fix, who've been using neural networks and satellite imagery to nowcast the movement of clouds over the next 2 hours so that they can get more accurate short-term solar PV forecasts. They've managed to increase the accuracy of the forecasts by almost a factor of 3, and this will directly feed into lower costs for you and me. EPRI have focused on the longer term, running a competition called Learn to Run a Power Network. This involves much smaller, much simpler networks, where the goal is to train reinforcement learning algorithms to learn how to run the network and balance supply and demand. So those are 2 examples of how AI is at work in the energy sector. But the reason I painted the whole big picture for you is because I want you to get excited about solving some of these problems. Pushing state-of-the-art forwards on time series analysis and dynamic graphs is really important to the energy sector. Maybe you work in a different sector and some of this sounds familiar to you and you have techniques that you think would be useful. Come and share them. Or maybe you're looking for your next research project. Well, there's lots of fun and impact to be had here. Or maybe you just want to play around with some new data and tools. Whichever it is, I'd love you to get in touch with me so I can introduce you to my friends, whether those be data sets or people. Thank you.
Right, thank you very much, Sam. And we have a few minutes for questions and answers. So we have one question that's just come in on Slido. Isn't one way to match supply and demand by using dynamic prices, matching utility for provider income minus production cost with consumer electricity need minus cost? So perhaps you could comment on. Well, this is something that I've discussed with others as Energy Systems Catapult, this question of how we do this matching of available supply and available demand and time shifting across the whole energy system, from domestic consumers up to the largest generators.
Yeah, and one of the likely ways that we're going to do it is using price signaling, right? So trying to enable people to pay based on how much energy they need. And as I say, that has a whole load of complexity to it. So to some extent, there's a role for AI in there. You're unlikely to be sat there at home going, I wonder when I next need to reduce my demand. You're probably more going to want to have some kind of system that automatically keeps your energy costs low but allows you to go about your day-to-day usage. And so again, kind of like AI agents that can intelligently understand your preferences and respond to price signals in the market. That's another opportunity for AI, and we're starting to see some of that kind of coming in, but it is dependent on the market as a whole and kind of the granularity with which we send price signals being in place, and that's something that's being looked at in government at the moment.
Yeah, and I don't have any more questions in the Slido, but I'd actually, again, myself like to ask a similar question to the one I posted after the first talk. So, I mean, I think most would agree that AI and data science skills historically haven't been very widespread in the energy sector, and I'd be interested in any thoughts you have on technology adoption in that context, and where you have a limited number of specialists and a much wider range of users, and how that sits both in terms of skills and skills and this sitting within organizations, and then how we move from where we are now to where we need to be if we're going to realize our ambitions for the energy sector.
Yeah, and I think the observation that I'd make to avoid repeating ones that have been made before, but is that a big part of the challenge is that the system is a network or a set of networks, right? And I really like Conway's law, which is that any IT system resembles the organization that designed it. And when you have a whole network with lots of different organizations all kind of like running different bits of it, you end up with fragmented ways of doing things. And And so that's actually kind of a big part of what we've been trying to do at the Energy Systems Catapult, is to push for open data, for open models, for kind of sharing of the thinking, so that then people can kind of see the benefits and they can work collaboratively on that across the whole system. Because if you just solve the problem in a small part of the system, it doesn't really kind of work. You need to see the whole system and join it all up together. So that would be the kind of angle that I'd come at it from, is that open data and kind of open communication about how we're solving these kind of things can really help with the adoption, because everyone sees the benefits.
Great, thanks. And I think we've got time for another question. In fact, I'll actually take two questions together. There's this very specific questions about what kind of specific AI methodologies you're using, and the question gives the example of neural networks. And then there's a slightly wider question of any particular applications of use of AI and ML to maximize use of renewables as opposed to curtailing them. I'd be grateful if we could keep to about a couple of minutes, because we need to keep going.
Yeah, so on the first one, focusing on demand forecasting, it's really interesting to see the types of algorithms that are particularly powerful there. GANs are the most common. They seem to kind of like perform really well. But where there's kind of potential benefit is if you're doing that hierarchical forecasting, then you start to see kind of like gradient boosted machines and that kind of thing perform quite well across the whole hierarchy. So those are pretty common. The other thing I'd say in terms of like in the individual small pockets, there is research on applying neural networks, and particularly one of the challenges is if you're trying to forecast a single time series, like a house, but it's pretty similar to other houses, then you want that ability to kind of learn from all of the other houses and yet kind of fine tune it for that particular house. And so there's some work on neural networks there, and kind of how do you train across a whole population and refine based on that. So yeah, that would be my summary of what algorithms are being used. Remind me, Chris, what was the thrust?
It's just about, are there any particular applications of AI in terms of how to maximize uptake and minimize curtailment of renewable generation?
Yeah, so I think to some extent the open climate fix example that I talked about with trying to more accurately forecast some of the renewable generation is really useful, because the way that it works is we're going to buy the kind of non-renewable generation if we're not certain about the renewable. So that's kind of like a key application. I'm not kind of particularly aware of loads of like algorithms that are specifically determining what are we going to use for a particular time. I think it more currently is at that kind of level.
Thanks very much, and we must move on to the last speaker and to the Slido operator. Can we keep questions in Slido in case we have a little bit of additional time for Q&A at the end, please? So I'm very pleased to hand over to the final speaker, Mona Faraji-Neri, who's an assistant professor at Warwick Manufacturing Group at the University of Warwick, who's going to speak on machine learning for optimized lithium-ion battery manufacturing. So over to you, Mona.
Thank you, Chris. Thank you so much for the intro, and hello everyone, and I'm truly honored to be here presenting today. What I'm going to present today is part of our research, which is the application of AI and particularly machine learning for the and its challenges and obviously opportunities for the optimized lithium-ion battery manufacturing. A little bit on who we are. WMG is the Warwick Manufacturing Group, founded in 1980. It is made up of 5 directorates at this moment, and we are concentrating on solving the most challenging problems of our industry in UK, including energy, automation, electrification, and transportation systems. Our focus in energy directorate is facilitating a smooth transition to net zero by supporting electric transportation systems development. The research that I'm going to present today is part of the Nextdoor project, which is a consortium led by Faraday Institution and a collaboration between 6 UK universities, including University of Warwick. towards the manufacturing of next generation electrodes via smart and digitalized manufacturing techniques. So it is obviously pretty well known that the electric vehicles are already recognized as a major solution and a replacement for the internal combustion engine vehicles. And it's not just the vehicle, normal passenger vehicles, it's all about the aircrafts and also marine systems. According to the stats, there is already a major rise in the demand for EVs all around the world. The sales only in UK has been gone up from about 25k to about 300k in just 5 years. And the global EV sales in net zero scenario is expected to rise from about 5% of the share of the whole market of the EVs to about 70% by 2030. This all means that a steep rise in the demand for the lithium-ion batteries, which are the key technology for electrification of transportation systems, is happening at this moment. The capacity of lithium-ion batteries entering the global market is projected to increase more than tenfold between 2020 and 2030, driven by the growing adaptation rates of the consumer electronics, personal mobility solutions, and electric cars. It is expected that in 2030, lithium-ion batteries with a total capacity of about 2,700 gigawatt hours will be placed on the market, and the number is now around 185 gigawatt hours. Generally, a battery is made up of different components, among which the cathode is which offers the active material of the lithium ions, is the most expensive one to be produced, and cathode manufacturing has the highest share in the total battery manufacturing cost. Battery manufacturing is a complex and consecutive process. It includes mixing, coating, drying, calendering, cutting the electrodes, assembling electrodes, and electrolyte injection, formation, and finally testing. So each of these steps are associated with a large number of control variables and design parameters that should be decided before the actual manufacturing run. Factors such as the temperature of the dryer, the pressure of the calendering device, the drying time, and also the speed of the foils moving within the coating equipment, as well as mix and speed, etc. These all have a major effect on the quality of the intermediate products, which are the slurry mix, the coated electrodes, and also the final products, which are the battery cells themselves. And by that, we mean their capacity, lifetime, the power and energy density, their internal resistance, which affects their safety and also stability of cells in practice. Selecting the best combination of these control variables and parameters is quite a challenge, and our experience confirms that there are about 600 of those in a real manufacturing chain, and the optimization by trial and error, which is a very common approach at this moment, is very time and resource consuming. Considering that just about 10% of the investments are going to R&D and the product and process improvements, it is critically important to reduce the cost and waste and facilitate rapid prototyping. This is only applicable by moving towards predictive and model-based approaches. And within this concept, machine learning models can provide a solution, and they can correlate because they can simply correlate the large number of control variables and the responses in a more efficient way. Following this goal, the objectives of our project is to create a data-driven model based on AI and ML for different stages of manufacturing of lithium-ion batteries, and answering basically the question of what modeling techniques are suitable for this, and what is the nature of the data that are available or should be available for training and validating a model. So this is basically an overview of the steps that's been taken in developing such models. So everything starts within our labs when we collect our data. This needs to be done by a carefully designed experiment and the expert's view to define the ranges of the variables and the breakpoints, etc. And the data that we generate in our labs, we take them to the data management step. We clarify, we clean those data and make them ready for the modeling step. In the modeling step, it's where we go with the predictions, with the estimations. We use techniques such as classifiers, multivariate regression models, and deep learning models. And the purpose of these models is to define the category to which a product belongs based on its specifications, or just directly predict its characteristics, such as its energy capacity. And then the final step, which is also very important, is to provide feedback to the manufacturing line through the interpretation of those results and through conveying those findings to the line again. The data that we get through these manufacturing lines come in different formats. They're temporal data, tabular data, categorical data, and also image data. And we use a combination of those within our models in order to predict the response variables given our control variables. Here I have two very simple examples of the models that we have developed in the past 3 years. So the first one is when we can predict the electoral features such as thickness, porosity, and its mass loading, maybe given the control variables. And also the other one is when we predict the energy capacity or internal resistance given the characteristics of the electrodes and the control variables altogether. And this line of research has also helped us not only to build predictive models, but also to take steps in order to explain the manufacturing steps a bit more than what we had based on trial and error. And it helps us by explaining explainable AI techniques, explainable ML techniques, actually, to understand the interaction of the variables, the impact of those on the responses, and also the dependency and correlation analysis. This line of research has a number of impacts for us. It is offering prediction of the responses, interpretation of the relationships. It helps to identify critical parameters and facilitate the model-based quality checks, which is particularly very important where the experimental quality checks are costly or hard to run. The research is still going on, and the main focus is taking these models from lab and pilot scale, which is what we have in WMG, to real industrial scale. And there is work to do to gain the manufacturer's trust in models and encourage those to replace some of those hard to run or expensive experiments or repetitive ones with model-based predictions. So this scale-up challenge is about generalization, robustness, and adaptability of the models. Thank you for listening, and please do get in touch if you're interested in this project.
Okay, thank you very much, Mona. We have about 5 minutes for Q&A to Mona and any of the speakers. I don't have any questions for Mona yet, but please put them in Slido if you have any. But there's still some more for the energy systems catapult. So one question that I think a lot of people are interested in, and I'd be grateful for any comment that you have, is that National Grid have launched their plans for an energy grid digital twin. And do you have any knowledge of how that might be able to help the AI agenda and help develop AI applications in the energy sector? That's a question to Sam, if he's still here. No, I don't think we still have. No, we don't seem still to have Sam. I think we don't currently have any questions for any of the remaining speakers. I'll just briefly wrap up and see if any come in the meantime. But I'd just like to thank all the speakers again for their contributions. I'm sorry for various tech issues that meant that we ran a little bit over time. So if there are no more questions, then I think it's best if we finish around now to give people a little bit of time back for a break. So I'd like to thank the speakers, and I'm sure in those attending live in the audience will thank the people on stage in the traditional manner. So with that, I still have no questions to ask. So with that, I'd like to finish the session, and hope everyone has an excellent day at the rest of AI UK.